All right, hello. So today I'll be presenting the ECE 277 final project. The topic I chose is parallelization of Q-lambda learning. So let's go over a little introduction about some motivation about why I chose this topic. So Q-lambda learning is generally believed to outperform single one-step Q learning, since it updates the Q matrix through evaluating past experiences. So it is generally believed to be faster, and since we have already implemented Q learning in Lab 3, I wanted to see if implementing Q lambda would be possible and if I could make it even faster. So the goal is to implement asynchronous multi-agent Q lambda learning, and then after we will compare its performance with asynchronous multi-agent Q learning. So here's a little bit of background. So as I said, I'll be extending what we implemented in Lab 3, which is Q learning, asynchronous multi-agent Q learning. So we have the same setting. I'll roughly go over this. We have 128 agents, a 32 by 32 board, 96 mines, and one flag. So we have random generation of the agents. We try to update a singular Q table through state action transitions. So there's also different types of Q lambda. And in Bartow and Sutton's reinforcement learning book, he mentions Watson's Q lambda learning, Peng's Q lambda, and naive Q lambda. So in Watson's Q lambda, we cut the eligibility traces, and I'll go over what that is. But early on in training, we cut the traces when we're doing exploration. And then in Peng's Q lambda, we actually back up the max action at the end, and we never cut traces. This one's a little bit difficult to implement, according to Bartow as well. And then for the naive Q lambda, we back up the max at current action. Here is a diagram of Watson's Q lambda. And then here's also an implementation and pseudocode of Peng's Q lambda. And now I'll discuss a little some of the differences between Q learning and Q lambda learning. So Q learning can actually be generalized as Q lambda learning as a special case where lambda is 0. And then for the parameters, we have the learning rate, the discount factor, and for both, and then lambda is special to Q lambda learning. So here's a little bit of background about eligibility traces, since this is a main component of Q lambda learning. So when a TD error or a terminal state occurs, eligibility traces keep responsible the states and actions that are to blame for the error or the reward. And using these traces, we update the entire path simultaneously. So where Q learning only updates the most previous step, eligibility traces can explore a bunch of states and then update them at once. And so in this picture on the right, we can imagine a user reaching a state after many steps, and then updating, well, we can call this backing up all the Q values and updating the Q function, or the Q table. And by setting lambda, we can control, it can be thought of as the strength of your voice decreasing. So with a very high lambda, you're making more of an impact and updating the previous experiences more strongly. And there are different types of traces, namely accumulating, replacing, and Dutch. And for my implementation, I'll be using replacing, as accumulating traces can have some issues, such as doing poorly on certain types of tasks. For example, on the bottom right, we have a task where a agent can keep going on the wrong direction. We have a linear binary choice of going right or wrong. If a user keeps going to the wrong direction, they can keep updating that value, and it can be stronger than the right value, and eventually it will converge, but it will take a much longer time. So replacing traces it performs better. So here is the algorithmic view for both algorithms. On the left, we have the Q learning algorithm, and then for Q lambda, we have a new variable here called E, which is the eligibility traces. So here's the problem statement. Some critical questions are whether we can parallelize Q lambda, and how can we parallelize eligibility traces. So looking at the algorithm, there's some opportunities where we could probably introduce parallelization, such as this for loop here. And other than parallelization, what other optimizations can be introduced from the CUDA side? And then the chosen problem statement is to implement Watson's Q lambda, and then also use replacing traces. So next section, I'll be going over the strategies. So firstly, for a single agent, we can imagine the scenario where we have to update Q with E. So looking at the pseudocode for Watson's Q lambda, we see that we have opportunity to employ matrix addition, where here we have Q plus ESA for all states and all actions. So we're basically adding Q by E, the entire matrix. And then here we also have matrix set. So we're just setting E to be 0, the entire matrix. And then also we have matrix scaling. So we're multiplying every value in E by a scale factor. So key observations are that we can update Q with E, and this perhaps means that Q and E can be the same dimension. Next, for asynchronous multi-agent Q lambda, One observation is that now we have 128 agents, and we cannot simply have dimension of E equal to dimension of Q. This is because although we have one Q matrix for all 128 agents, we can't have one E because each agent should have its own trace. For example, here, when we take a non-greedy action, the trace should be set to 0, but if we set the matrix to be 0 for every single agent, then other agents will just lose their trace, so it does not make sense to do that. And then each agent will need its own trace. So here I'll go over the strategy for the Q table and kind of the thinking process of the data. So we have a 32 by 32 board, so we can embed this in the X direction as 1024, and then we have 4 actions which are up, down, left, and right. So we can put this in the Y direction, and this can be your Q table. Of course, this will be actually just a linear coalesced memory in memory. So we use a linear index to so when we initialize the Q table, for example, we can just set it all to 0, and we can use this kernel function to initialize the Q table with 8 warps. So in our pseudocode, we see that we have to find the maximum action, and one way to do that is to take the argmax. And to take the argmax of this table, we can simply, for a given state, look at the best action. So each of these rows embed the entire state, and we can just take the argmax along the Y direction. So here's the code that shows implementing that. And now for the E matrix, we can have a 4096 dimension X and a 128 dimension Y. So the reason we have 4096 is because we want to embed entire Q table into one row, and then for the 128 will represent the agents. So each agent can have its own entire row, and when we update our traces, we can update one row. So that row will be responsible for matrix addition. So for example, here when we do update the trace, we say we do this operation here where we do Q equals to Q plus some scaling of E. Then we can scale this part of E, and then we can just add it to Q, and then we do this for every agent. So Q will be updated 128 times by this E matrix with addition. So that was the strategy 1, but there's a problem, and it's that E matrix ends up being very large, and it gets up to 128 times 4096, which is 500,000. Also, E is sparse, so most of the threads are adding 0, especially early on when we're doing exploration. A lot of the agents will be just hitting mines, so then E will be a very sparse matrix. So we're doing a lot of redundant addition. So strategy 2 is to use a E-trace struct rather than a matrix. So we can borrow the idea of using an array of structure, and we can update only traces that are non-zero. We can have this struct here, and we can have different variables. Here we have trace length, which we can define as just remembering our previous, how many steps we have taken, how many traces we have. And then with this, we can reduce the time complexity from O of n to O of m, where n is the state action space times number of agents. So the entire size of the E matrix to just the length of, to just trace the trace length times the number of agents, the max trace length times number of agents. So we create a array of structure, a E trace of 128. So it's almost a array of structure of array, since we have these here. So first we have the trace length, and then we have X, Y, and past action, which stores the history of the state. So X and Y will store the history of the state, and action will store the history of the actions. And then E will actually just store the eligibility trace values. So when we want to update say we want to update a current agent, we can just look at how many traces there are, and then we can just look at the index in X, Y, and past action to retrieve the Q index. And then once we have the Q index, we can update Q at each Q ID. So we can update Q trace length amount of times. So say our trace length is 5, we can update Q 5 times. We don't have to update it by the entire E matrix. And then also when after we update Q, we can also update our traces by the decaying factor of lambda, and we can do this by shifting the array. So because E is equal to E times lambda, we decay it. We don't have to actually multiply the entire matrix, scale the entire matrix. Rather, we can just shift this array one to the left, multiplied by, and then we use trace length as the index to tell us what where we access X, Y past actions in E. And then when we reset E, we don't have to actually set everything to 0. Instead, we can just set trace length back to 0. So here's another detail of the implementation. There are actually some different variants we can choose. Just like in Lab 3, we don't actually implement the pseudocode exactly because we have 3 different rewards indicating different states. So when we capture a mine or capture the flag or step on a mine, these are terminal states. So for the mine, we can choose to either back up or not back up everything, because most of the there's a lot of mines. So we can use the original Q learning backup, one-step backup, instead of updating the entire trace if we want to. And I've tested both implementations, And then for the flag, it's we should always back it up. And then for when we don't step on anything, we don't have to back it up. So now I'll go over some strategies on optimization. So one strategy we could use is to reduce ALU operations in the kernel function. So we want the CUDA cores to avoid as much like unnecessary operations. We can do this by hard coding values instead of like leaving them as multiplication. Like for example, the 32 times 32, we can just have 1024 there instead. Secondly, we can use the golden rule of how many warps to put in a thread block. So 2 to 8 warps. Thirdly, we can try to have as much coalesced access, read and write with shared memory. And then fourth, we could use sync threads to avoid race conditions within shared memory. And then fifth, we could use shared memory and shuffle operations to find the argmax quickly instead of having to loop through have a for loop. But in the case that we have to use a for loop, we can use pragma unroll, which is an optimization for the compiler to have just to optimize for loops. Lastly, also we can declare variable types in the beginning to avoid type conversion overhead. And then lastly, we can organize our code structure to not execute code that is that could be put in if statements if the else statement is not using the necessary variables. So here the bold bullet points are the ones that I ended up implementing. So unfortunately, I wasn't able to optimize it with shared memory. Here is an example of here's also an example of pragma unroll, where a for loop such as this in the compiler optimization ends up being this. So now I'll be going over the code walkthrough. So let's get to the interesting part, the update Q-lambda function. So this will be the update function, and for this kernel, we have a thread index which is to 100, goes from 0 to 127. So this will be just a kernel of 128 threads, and then we just check if we're in bounds or not, and then we check if our agent is active. So only after all this do we consider the rest of the code. So firstly, we using the picture that I drew earlier, we can think of it as a 4 times 1024 rectangle. So then we look at the current action, and then we get the since we're given the current state and the next state, we get the xc and xn for x current x and current x for current and next, and then we can get our current index for q. So next we'll be getting the argmax and the max for the next state given our q table. So first we just set it to our base index, and then we just we take the argmax over each row by adding 1024 to the index every time. Instead of actually, we first update the trace. In the pseudocode, we actually first update q, but since we have to actually get the current eligibility trace, we can first update all these parameters. So for index, we just we get our current trace, and then we update our past actions to the current action, and then our current state x to current state, history y to current y, and then also and then after all that we increment our trace length by 1. And after we have our eligibility trace variables updated, since this is actually a current trace, we actually start from current step minus 1, which is our previous state. So having the previous state, now we want to update our Q matrix with every action in our history. So then we get our Q index, as we said, and then we can add it on. And lastly, we can update our eligibility trace by decaying it by gamma times lambda. And also we disable the agent, since this if statement is if we either catch a mine or a flag. So since these are both terminal states, we have to disable the agent. And then also when it's neither a flag nor a mine, we have this update function for Q. So interesting to note is that we have gamma and max. And we have max here because since we're still non-terminal, we can still have further actions. Whereas here in delta, we actually don't have the max variable here because there won't be any future actions. Lastly, this here we just check if the current action is actually the optimal action. So if it's not, that means we took a greedy, a exploratory action. And because of Watson's Q lambda, we have to set the entire E matrix to 0, but instead we just set the trace length to 0, and we just set the entire trace to 0. So we just go from n, where it's a trace length, all the way to 0, and we set everything to 0. Okay, so next I'll be going over the demo. So you can see that I'm using the same code as the one I just walked through, and then we have update Q lambda, which is what we just talked about. And right now I'll be running Q lambda. I also implemented update Q for comparison later. So let's run. Okay, so now it has reached episode 200 plus. So since our delta epsilon was 0.05, we always follow we have no chance to explore random actions. And you can see that all the agents do converge to the flag. So now we'll be going over results and analysis. First we'll talk about performance metrics. So how are we going to evaluate the performance and the results? So different metrics we could choose, firstly, include using n-site compute to look at the profiler. So we can kind of check how much occupancy our CUDA program is at. And however, I couldn't really get this one to work because attaching n-site compute profiler, using n-site compute didn't really work because there wasn't a .exe file being built. It's instead just .lib. And also the default n-site profiler is deprecated in Visual Studio. Thirdly, we could use kernel execution time to determine how efficient our kernel is. And lastly, we can also, for the algorithm's performance, we can look at the steps per episode. And so with a delta epsilon of 0.005, we have 200 episodes, as we said. And we can, during each episode, we can accumulate the amount of steps, and even if until 20% of the agents are active. And we can save the number of steps into an array of 200. And then after that, we can save this array, and I generated these plots here. So I did 3 tests where I used Q-learning and Q-lambda, Watson's Q-lambda. And interestingly, sometimes Q-lambda is faster, and sometimes Q-learning is, not faster, has more steps per episode. And this here is the total amount of steps in the test. And this is 1, 2, and 3 respectively. So the analysis of this is that why this is happening is because of the random board generation. So because the algorithm is so dependent on where the spawns are, so if the flag is in a difficult spot, it's going to take more steps per episode to reach it. And same with the mines, if they're like very clumped up around the flag, same thing will happen. So, and since the board generation is random, we cannot use it as a controlled experiment where we use Q-learning and Q-lambda on the same board. So no conclusions can really be made since their fluctuations are larger than the differences in their performances. Secondly, for kernel execution time, we will be measuring just the kernel execution time of update Q, which is inside the CPU function agent update. So to do this, to implement this, we will use CUDA events, and we can actually just use the running average instead of just the kernel execution time every time. So we just have a running sum, and then we just increment the amount of steps, and we just divide it. Here on the right, this is an example of like printing the execution time and average time. This is for the Q-lambda. And then here, this block here is for the Q-learning, and these are the results on the right. So we can see that and these values here are the final values after converging, so after 200 episodes, and they tend to decrease until 200 episodes. So first thing to notice is that there is a significant difference in kernel times between Q-lambda and Q-learning. This is expected behavior because in Q-lambda we have the eligibility matrix being adding a certain amount of time complexity to the kernel with the for loop and updating the traces. So, and then secondly, for the optimizations that we mentioned, implementing all of them didn't really affect the kernel average execution time by a lot. Not enough to see a big difference in the randomization of the board itself. So randomization of the board also does fluctuate the kernel average execution time. And there wasn't a significant difference after optimization. Perhaps if we implemented more features, it would be more of a difference. So lastly, for future improvement, we could implement smart parameter adjusting, such as adjusting lambda for faster convergence. Right now, everything is just using 0.9. Secondly, we could also adjust the learning rate alpha and the discount factor. We can kind of tweak those values. And lastly, we could use dynamic epsilon update to update the episode, epsilon based on the episode. So lastly, we can use a shared memory cache of floats, of 4, and then we can kind of because we calculate the argmax of a state during the action, we can use that cache to do some sort of argmax with either shifting or some type of reduction argmax. Lastly, if I could also create my own environment, in this way I could test out like how much more efficient Q lambda learning is in terms of the steps per episode. And lastly, also implement Peng's Q lambda. Yeah. So yeah, thank you very much.